Alright folks, we're going to talk a little bit about electromagnetic radiation. Now, first of all, let's talk a little bit about, like what do we mean by electromagnetic radiation? The light that is coming from your computer screen is an EM radiation. The light from the light bulbs is an EM radiation. The heat that you feel standing next to a campfire is an EM radiation. X-rays, when you have an X-ray produced, like maybe to see the skeletal structure of a body, that's another form of electromagnetic radiation, right? So these are all examples of one thing. They're all electromagnetic radiations, what we call light, and what is an X-ray, and the heat coming off a fire. They're really all the same thing. They're all electromagnetic radiations. They just are in different forms, right? And they have slightly different properties. We're going to talk about that for the rest of this unit. Now, for starters, when we talk about electromagnetic radiation, the first thing you have to realize is that light has what's called a wave-particle duality. Radiation behaves both as a wave phenomenon and a particle phenomenon. So, for example, if I have a flashlight here and I turn that flashlight on, there's really two different ways to think about that beam on the light coming out of there. One, we could think of it like some sort of wave phenomenon coming out of the flashlight. And the second way to think about it is a stream of particles coming out of the flashlight. And oddly enough, both, it turns out, are correct. Right? So, the wave property of electromagnetic radiation. Some important properties of waves. Waves have a certain frequency, like I talked about in the last video. They have a certain wavelength. And again, remember that that's denoted with this letter, the Greek letter lambda. Right? This would typically be measured in meters. And waves travel at a certain speed, v. Now, this speed generally depends on the type of wave. For electromagnetic radiation, that speed is the same. X-rays and the heat coming off of the fire and what we call light coming from the bulbs all travels at the same speed, 3 times 10 to the 8th meter per second, or 300 millimeter per second. That's referred to as the speed of light, and it's one of the important fundamental concepts or constants of nature, and for that reason it has its own letter attached to it. So when you look in the back of the book, when you look this value up, it'll say C equals 3 times 10 to the 8th meter per second. Now, in the previous video, I talked a little bit about an equation that links the frequency to the wavelength. Right? And the equation that links the frequency to the wavelength is velocity is equal to frequency times wavelength. So, for electromagnetic waves, the V is the same. It's equal to C, the speed of light, 3 times 10 to the 8th meter per second. I want to talk a little bit about this equation and kind of the qualitative consequences on light as a wave phenomenon. I wrote a little example up here in the upper right-hand corner that kind of illustrates this. Look at the equation x times y equals 12, and consider all the different possible solutions of that equation, and hopefully I wrote them down correctly. Now, one possibility is that x could be 1 and y could be 12. That would solve it. Or maybe x is 2 and y is 6. Or maybe 3, 4, 6, 2, 12, 1. These are all possible combinations of x. I'm sorry, this isn't all of them, but these are some of the possible combinations of x and y that solve that equation. What I'd like to point out is this. When x is relatively small, you notice that y is relatively big. Right? And then as x gets bigger, y gets smaller. Right? This equation behaves just like that, because the left-hand side of this is a fixed numerical value, c, 3 times 10 to the 8th meter per second. So what that means is if the frequency is relatively small, the wavelength is relatively large, long wavelength. When the frequency is big, small wavelength. That's one of the very important fundamentals of radiation. Small, or short frequency, corresponds to long wavelength, and high frequency corresponds to short wavelength. Right? We'll talk more about that later. Right, now let's talk about the particle nature of light. It turns out that, if I had a detector over there that basically went beep every time you turn the light on, what scientists found is that they would set up a detector and take something like a flashlight. Now, they didn't exactly use a flashlight, but humor me for the discussion. So when they turned the flashlight on, the detector would be going beep fairly continuously. But what they were able to do is turn the intensity of the flashlight down. And what they found is that the detector behaved more like this, more like beep, beep, beep. It had these gaps in it. And then if you turn the intensity down even further, the detector would go more like beep, 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 and that's registering individual, what we would call particles of light. Right? So that's kind of the experimental evidence for light behaving like a particle. And you've heard this before on TV where you've seen things like people using what are called Geiger counters, and they actually kind of tick. You know, they kind of go tick, 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 or beep, 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 when they're registering some sort of X-ray radiation or some sort of high-energy radiation. So those particles, those little particles of light, they're called photons. There's kind of a symbol for a photon. It's kind of this kind of short little scrunched up wave. And the important thing to recognize about photons, you can think of them as little particles of light, but they have the following properties. They're particles that have a frequency, a wavelength, they travel at c, the speed of light, and they also have an energy associated with that. That depends on the frequency. In fact, mathematically, this is how it depends on the frequency. The energy of a single photon is equal to h times f, where h is a value called Planck's constant. And it's the same value for all electromagnetic radiation. This is another one of these fundamental constants that do not change. And we'll talk more about what it is in upcoming videos. So that's a little bit about electromagnetic radiation. Now, an important thing, it behaves like waves, which means it's got a frequency and a wavelength. Travels at c, 3 times 10 to the 8th meter per second. It also behaves like particles. The particles are called photons. So you can think of light, I like to think of light or radiation as a stream of particles that have wave-like properties. So everybody, I hope you enjoyed that, and we'll move on and I'll make another one.